Solutions, we're going to look at how solutions form. So the first thing we have to do is look at what makes up a solution. Remember, homogeneous means that it must be uniform throughout. And that means from one end of the solution to the other end of the solution. Okay? And that means that we have to pretty much operate at the molecular level within the solution. So when we talk about things mixing, we're going to have our solvent and our solute separate and mix up uniformly here. And this doesn't look beautiful, but it's my attempt at uniform. Okay, so that's the first aspect. And remember, we're back to like dissolves like to figure out of your text. So notice that dispersion forces stick together, dipoles stick together, hydrogen bonds like to stick together, and ion dipole like to stick together. So when we look at this, we're actually looking at three sets of interaction. We have our solvent and our solute interactions. These are before you make the solution. And then the only one we have after solution formed is where you have the solute interacting with the solvent. So we've got to look at these solution interactions, and remember real quickly, we have London dispersion forces, dipole ion, and hydrogen bonding. So we're going to look at these interactions as we go. So if you get to this point and you saw that, but you're like, wait, I don't remember, I've slept, go back and review the intermolecular forces before we get started. So we're talking about solution formation. We basically have three steps. First one is you're going to break up the solvent into its individual particles. This takes energy. It's always endothermic. Breaking up the solute particle, think of separating magnets. You have to do work to separate them. This is always endothermic as well. Now, the attraction of the solute solvent particles is always exothermic. However, how exothermic it is can vary. So remember, this would be positive, this would be positive, and this will be negative. So the delta H of formation of the solution is determined by how much energy it takes. So here's a figure here. These are all the solvent particles being separated into the individual. Remember, that takes energy. And then the second step, we're going to take all the solute particles, put it in there. Mixing, this comes out negative. So the difference between my initial state, which is the solute and the solvent, versus the final state will give you the delta H solution. And in this particular case, because you need more energy to go in than you get out, so delta H is positive, this is an endothermic solution formation. Now, on the other hand, it's up here in big letters. So, on the other hand, same steps, again, positive, positive, but this one's negative. But here, your initial state, your final state, delta H, here is less than 0, so it's negative. So, this is an exothermic reaction. Solution formation. Now, some things you can actually feel. The ice pack, that is definitely endothermic. You can buy the little hot packs where you snap the little metal piece. I have some in lab. I may try to put a picture up. When that process occurs, it's very exothermic, so those are warm. So whether it's endothermic or exothermic is a function of the solute and the solvent particles and how they interact. Okay? So, this is a similar text from your book, and it shows you again an endothermic and an exothermic. It stacked them side by side, which may be easier for some of y'all to see. So here is a different Pearson text. This basically is showing you hydration or solvation again. Remember, it's hydration because it's water. And notice that this is an ongoing process, is that crystals will keep forming as long as there's a crystal present, but they will dissolve at either a faster rate depending upon the concentration level. Okay? And so if you totally dissolve, you're going one direction. If you've reached saturation point, you've got a dynamic equilibrium. So this is a saturated solution. This is an unsaturated. Okay, so let's work a problem to figure out how things work. So list the intermolecular forces of the species present, then choose the better solvents each for the following pairs. All right, so I'm going to start here. This is CHHCl. Cl. Okay, so this has London forces. It's actually an unsymmetrical molecule, so it has dipole. All right, methylamine, which is CaH3, NHH, which has the lone pair. It will have London forces. It will have a dipole, and these here will allow for hydrogen bonding. So we have the intermolecular forces of our solvent. Now let's come back over to lithium bromide. So let's look at the intermolecular forces here. So obviously it has London forces, right? Wrong. This is a salt. This is an ionic compound. So then it says which one is the better solvent. So remember, like dissolves like. So because we're looking at the dipole, what we're looking is going to be a dipole ion. So we want the strongest dipole, and that will be on the ammonia because it's bigger. So the best solvent will be the methylamine. Again, you don't have to know that that's the name of it. So we look here, we'll start here. This has got nothing but carbons and hydrogens, so it's lithium fluoride. Ha! It's London forces. This has got carbons and hydrogens. This happens to be known as benzene as a compound, but it's only got London forces. This is methanol. If you notice, it's got London forces. We have that carbon OH, which means we have a dipole. And because we have the OH, we have hydrogen bonding. Now, since the rule always falls down to like dissolves like, then we're going to say C6H6 is our better solvent because it has similar intermolecular forces. They are both London forces only. So as a matter of fact, that butane here really will not dissolve in methanol easily. So do another one. Answer the following using the compounds in the lists of compounds below. So again, we keep like dissolves like in the back of our head. And we're going to look at intermolecular forces. This is a carbon, an oxygen, and a carbon. So we have London forces. And we have a dipole, but we have no hydrogen bonding. Now, this is an ether. And ethers are universal solvents because even though they can't hydrogen bond, excuse me, with themselves, second hydrogen bond with other compounds. This is a salt. This is CH. So we know it has the London forces. We know it has a dipole. Does it hydrogen bond? No hydrogen bond because the hydrogens are not attached to an electronegative species. So on this one, we have this lots of carbons, and then we have a chlorine. So it's mostly London forces, but has a little bit of dipole. It has no hydrogen bonding because there is no hydrogen bonded to an electronegative species. And then we have CI4, which is similar to CCl4, which has London forces. It has polar bonds, but it's a perfectly symmetrical molecule, so it has only London forces. Okay? So, now the question is will it dissolve in water? Well, water has London forces, dipole, and hydrogen bonding. So, the first one will because it has a dipole. The second one will because it's a salt, rubidium sulfate. H2CO has dipole. And when we look at this compound here, this is really mostly London forces. So it might be partially miscible, but not probably very good for CH3, CH2, CH2Cl. Most likely it is not going to dissolve at all. Now, on a test situation, I try not to give you samples that are ambiguous. I try to keep to species that are kind of obvious. So don't sweat the small stuff. That's why when you go to work the problem, if you show me your work, even if you have it wrong, but you have it wrong for justifiable reasons, you won't get all the points back, but you'll get some of them. So that's how partial credit works, is you got to show me the work for problems that are in debate. Okay? Now the other one says, what will dissolve in carbon tetrachloride? We know that that's London forces only. So the beauty of this one is, hey, we know this one will go here. This is propylene chloride. I added too many carbons on. No, I didn't. And carbon tetraiodide. And if you'll look, this ether has an even amount. This got the 2CH3, so actually it'll dissolve in both. That one's the kind of the tricky one. So again, if you show me your work and you have something slightly different, I will look at it with respect to partial credit. So that brings us to another intermolecular force problem. It's using the principle like dissolves like. Predict whether ethylene glycol will dissolve in gasoline. Well, gasoline is a variety of compounds, but it is C8H18. So gasoline is London forces only. That's why it vaporizes readily when you're filling your gas tank. And if you're looking at the ethylene chloride, I'll write it like this so you can see a little bit easier. But look at all the OHs. It has London forces, it has dipole, and it has a lot of hydrogen bonding. Ethylene glycol used to be used as antifreeze because it's very syrupy and very sweet. So if you look at these intermolecular forces, will it dissolve in it? And the answer is no. Ethylene glycol will not dissolve in gasoline. Molecular iodide dissolves in carbon tetrachloride. This has London forces. This has London forces. Neither of them have dipole. They have polar bonds, but they're symmetrical. Iodide is self-bonded to iodide, so it doesn't even have a polar bond. So the answer on this one is they have the same intermolecular forces, so the answer is yes. Motor oil is a combination of carbons and hydrogens. So remember, all carbons and hydrogens are nonpolar. So that'd be London forces. We did carbon tetrachloride before. Oh, and then B, if you remember back to that slide before, I told you that it preferred it to go into carbon tetrachloride. It's London forces only. So the answer on this one is yes. Okay, so depending upon how it's asked, you can get different answers, because I could have said, will it not dissolve? Now, that would be least likely. I'd be more likely to have done that on the previous one. Okay, so that brings us to fat-soluble and water-soluble vitamins. I highly recommend you reading this section, because assuming you're reading this, you're a human. And so vitamins are very critical. And this is, you can see in here why settlers are called limeys. Okay, so another thing to look at is that the solubility of different solvents will vary with temperature. For solids, they're going to generally increase the amount as the temperature increases. So as you'll notice, the temperature is rising here. And most solids increase. Sodium chloride is kind of flat. Okay, and there are a couple ones that decompose as they're heated, but those are rare. If you look at the majority of them, these increases. On the other hand, if you look at gases, they tend to decrease as the temperature increases. Okay, so as the temperature rises, their solubility is dropping. And this makes perfect sense, because if you've got a soda and you just poured it out in your cup and you're in hot weather or a hot room or whatever, the bubbles come out faster. If it's cold, ice cubes or a cold room, you hold on to the temperature, the CO2, a whole lot longer. Okay? Now, if the temperature rises and the oxygen comes out, we call that thermal pollution. This is exactly why if you've got fish at home and you change the water in the aquarium, you usually heat it up or boil it to drive the chlorine gas out. The side effect of that is that you drive the oxygen out. So if you let it cool down and you don't give it enough time for the oxygen to re-enter, then you can put your fish in there, but they can't breathe. So there are a couple ways to get oxygen in there fast. If you can mix it up with a spoon or some sort of stirrer, that will help. An aerator helps way faster, but that's why you have to wait overnight after you cool your water, not because the water's still hot, because you've got to give it time to oxygenate. So that brings us to Henry's law, which has to do with solubility and the pressure of gases. Now, Henry's law is the solubility of a gas is Henry's law constant times the pressure of the gas above it. So the solubility of the gas in meters. Okay? So you have to be given the Henry's constant. So if we're given a problem, we're told it's 25 degrees and our constant, so it's 1.166 times 10 to the minus 6 moles per molar, because that's moles per liter, per millimeter of mercury, because it's related to pressure. Suppose that a trout stream is at an equilibrium with the air at normal atmospheric pressure. What is the concentration of O2 in this stream? Well, we know that the solubility of a gas is equal to the Henry's law constant times the pressure of that gas above it. So we have our Henry's law pressure, mole per millimeter of mercury. And so what we need to know is the pressure of the gas. So what we need here is the pressure of the oxygen. So wait a minute. We said that it's the atmospheric pressure. So the pressure of oxygen is equal to 21% of 1 atmosphere. And remember, 1 atmosphere is equal to 760 torr, which is millimeters of mercury. So if we take 760 millimeters of mercury and we multiply it by 21, we know that in the atmosphere we have 159.6 millimeters of mercury that is strictly due to the oxygen. So we'll put it in here. And again, typos abound. So 159.6 millimeters mercury. So that means that we end up with 2.64939 times 10 to the minus fourth molar of the solubility of the gas. Okay, so that tells the solubility of the gas, but we want the result in grams per liter. So we want our solubility in grams per liter. So we know that we have 2.64936 times 10 to the minus 4 moles per 1 liter. And we want it in grams per liter. So we've got it in the liters, so that's not a problem. So we have to determine what the atomic weight is, and we know that it's 31.988 grams of O2 per 1 mole of oxygen. That means it's 0.00844748 grams per liter. So if you'll notice, I got a lot of digits. We did significant figures in 1211, and a lot of people hold tight to them, and they are important when you get to lab, but we're not in lab, and we're dealing with really, really, really small numbers. So I'm going to ask you to keep 4 non-zero digits after the decimal. I'm probably going to use more than that sometimes, but that's all you're responsible for. So if that's the case, we would report this as 0.008475 grams per liter. Okay, so this is how we would work a Henry's Law problem. I'm not sure we will have one on the test. I'm pretty sure I did one in mastering, only because if you've noticed, we're going to cover chapter 11. 12 is an outside of exam problem, which is posted, and 13, we're getting into the fun stuff. By the fun stuff, I mean, be afraid I like it. So it gets very complicated. It's the solution formation. So the point I'm making is make sure you're caught up with me. The last slide in this section is blood gases and deep sea diving. This is actually really interesting. Even if you don't dive, I don't dive, but if you do dive, you may very well want to read this because it's critical that you keep up with the gases in your tank, how much, where you're diving, etc.